implementations. He's called Cédric Vincent. He contributes to a nice project software called PRoot to create a user implementation of CH-root. CH-root you can use without being yourself root. And he is also interested by the Perl 6 specifications. Currently his GitHub avatar is the Perl 6 butterfly. So let's applaud Cédric Vincent and for his talk.
Thanks. So I'm Cédric Vincent. I work for ST Microelectronics in the Compilation Expertise Center. And today I would like to introduce you a couple of software engineering tools we wrote based on syscall instrumentation. Also, I would like to share our experiences in this regard, so feel free to meet me during FOSDEM. Let's start with system calls, or syscalls for short. According to the official man page, a system call is a fundamental interface between your application and the kernel. That means if your application wants to access, for instance, a file on your hard drive, to open TCP port, to create, to kill processes, it will have to perform a system call. On Linux, all resources are accessed through system calls. Everything but the CPU register and the memory that have been already mapped. Among all existing system calls, there are a really special one named ptrace. Ptrace allows one to observe and to modify system calls performed by other programs without privileges. This feature is available on every Linux kernel version. I like to say this is just like one system call to rule them all. So we decided to create some tools based on ptrace, what we name system call instrumentation. So the first tool is PRoot, pronounce PRoot please. The main feature, yeah, bad pun. The main feature is about platform mapping. With PRoot, you can map any file over any alternative location. So in this example, you can map your own version of hosts over the system version of etc host. Then the specified command, each time the specified command will try to access this file, PRoot will intercept the system call and analyze its argument. So, for example, if your command tries to open the /etc/host file in this example, PRoot will detect that the first parameter points to the remapped file, and then it will rewrite the system call argument to point to the user specified file. So this works with files and with directories too. One could consider the -m option of PRoot just like mount --bind, but without privilege. Now, what would happen if you try to map a directory over the / over your actual root file system? This way. It will just be semantically the same as chroot. That is, your command will not be run from your actual root file system, but from the specified one. For instance, if you try to run VLC, it will not start VLC from your host distro, it will start VLC from the /root file system specified there. So I assume here that there are a full distro in this directory. Once again, this is just like chroot, but without any privileges. You don't need sudo or anything like that. PRoot is typically useful to build, validate, and debug application in an alternate context. For instance, you want to create a package for Fedora, but your host computer is Debian, let's say. You just have to download Fedora root file system, PRoot into this root file system, and then just create the package as if you were into a Fedora distro. Now, if you try to PRoot into a root file system, you might get this message. the dash R option here is just like if you try to remap rootfs over slash, which is just an alias. This error is raised by the standard C library from the specified root file system. Each time a program starts, it tries to detect if the current kernel is compatible with the expected feature. So it tries to detect the current kernel version, and if the current kernel version is too old, you will get this message. This is not specific to proot. You will get the same with chroot or with other programs that perform the same kind of trick. However, with proot, we can make your kernel grow younger. So you can specify a kernel version with the dash key option, and proot will emulate all the missing features, all the features that are missing from your current kernel, but that are available on the 2.6.32, for instance, here. So let's say your command tries to open the foo file relatively to the specified file descriptor with the open at syscall. If you are running a 2.6.9 kernel, for instance, proot will substitute openat with open and will replace the parameter with the file descriptor resolved /foo. This is semantically the same, except this is not atomic, but it just works. This is semantically the same. Now, if you try to proot into a root file system that was not built for your architecture, so let's say you try to proot into an ARM root file system, Raspberry Pi, for instance, Debian for Raspberry Pi. However, your host computer is just an x86, you will get this error message. And once again, this is not specific to proot. You will get the same with chroot. And once again, we have a nice feature. So you can specify the CPU emulator. In this case, this is a QEMU user mode emulator for ARM. And then, each time you try to execute an ARM binary with the execv syscall, proot will detect that the first parameter is not binary for your host architecture, and it will prepend the QEMU user mode command. And this program, QEMU user mode, will translate on the fly ARM instruction into x86 instruction. With time, proot has become more and more generic, and it can be used today as an instrumentation engine. It has a clean API where you can add your own extension. The two previous features are extensions, and you can also use proot as a base for your own tool. So let's take as an example care. Care is heavily based on proot. However, it doesn't have the same purpose at all. Care is a short for comprehensive archiver for reproducible execution. In a couple of words, it will observe the execution of your program and archive on the fly all the files and directory before any modification. And at the end, you get an archive. You can share this archive with anyone else, and he or she will be able to reproduce the execution exactly in the same condition. This is typically useful to create reproducible bug reports, demos, portable apps. So, a simple example. Let's say I want to report a bug I can't build. This is just an example. I can't build Perl on my workstation. Obviously, if I try to share the command as is on the bug tracker, I might get a clause cannot reproduce. So you just prepend your command with care. You can specify an output file archive. Care will observe all these commands and archive on the fly everything that has been used. And at the end, you get the foo.bin file as specified. It's only 42 megabytes. It's worth saying it contains everything to reproduce on a different computer. This archive is self-contained. It is also self-extractable, so you can execute it. It will extract itself. And at the end, you will get 4 components. The README file, it explains what the 3 other components are. The rootfs directory. This directory contains all the files and directories that has been used during the initial execution, before any modification. The pre-root binary, statically linked, that will be used to isolate the re-execution into the root file system. And the reexecute.sh script. This script resets all environment variables and starts the initial command with pre-root isolated into the root file system. So if you re-execute the content of this archive on a computer, let's say, that doesn't have tar, that doesn't have GNU/Make, GCC, that has almost nothing, it will work because all the commands and the program are accessed from the archive root file system. It's worth saying that care doesn't require any setup or any privileges, both for archiving and for re-executing. And for the re-execution, you don't need any external tool. Everything is contained into the archive. We wrote more extension and more tools, and this is a lightning talk. I don't have the time to explain all the tools, so just a couple of them. First is an extension. It is currently built into pre-root. You can enable it with the -0 option. It fakes root privilege. Actually, it fakes the root ID, but also the root's behavior. This is required when you try to install a package into a root file system, because most package managers assume you are running as root and perform a sanity check. So if they detect that you are not running as root, they just abort. DevTracker, this is a tool based on pre-root. Just like care, it observes the execution. However, it doesn't produce an archive, it produces a dependency graph. So, for instance, if you have a build system broken when you try to build in parallel, you can just run this build system sequentially with DevTracker. DevTracker will compute the actual dependencies, and it will be able to produce a highly parallel GNU/Make file at the end, because it has observed the dependency, so there are no error. It can't introduce error because it missed something or other. It has observed everything. The third tool is PSTrace. This is a proof of concept to demonstrate the current API in pre-root. This is just like strace, but a little bit more eye candy. And you can add your own extension and you can create your own tool based on pre-root. So if you need details, if you need support, feel free to contact us through this website. I'm at the end of the talk, and I guess I have some time to answer questions or to get comments. So please.
Does the care toolset also emulate the time?
Sorry, I didn't understand.
Does the care toolset also emulate the time, record the time and replay the time?
No. But it could be. It could be added if it's required. Actually, we are able to reproduce a build of embedded distro with care. And so we didn't hit any issue in this regard. So, but if this is required, we could add some emulation timestamp and so on.
But it would be possible to emulate the time as well?
Yeah.
We have another question at the left, and then one at the rear. Here you are.
Seems to me that can care work with a multi-threaded program? I can't see how that would work.
Sorry, I don't understand.
Does care work? Does care attempt to work with multi-threaded programs?
Occur what?
Multi-threaded programs. I mean, how do you make that? How do you try to make that the execution reproducible? It doesn't seem like you can do that.
I don't understand. Sorry. Ah, yeah. It doesn't care. Doesn't care about multi-threaded programs. However, if you try to re-execute then if you have some, for instance, a race condition with a multi-threaded program, it will not reproduce the race condition.
Well, not just that, but even if everything is correctly serialized, things could still happen in a different order. The serialization could.
I don't understand, sorry.
Even if you're serializing operations correctly, they could still happen in a different order when you try to rerun the program.
Yeah.
So then it's not reproducible at all. So for multi-threaded programs, it doesn't actually.
Care is not about to reschedule or force a schedule during the execution. So if you have some race condition, they might appear or not, but this is not the kind of bug report you can archive with care.
And the other limitation I would expect is ioctals. You have to know. Presumably, you have to know about all the ioctals that are used. Otherwise, you can't record. You don't know what areas of memory could have been changed.
Sorry, I don't understand. I don't hear you actually.
I'm assuming that the record includes all the changes that each system call makes to memory.
No. It doesn't contain any change because it archives before any modifications. So, for instance, you try to archive a program that modifies your file system. Care will stop the execution right before the syscall, right before the modification, and will archive this version of this file. So, when you try to re-execute, it will re-execute in exactly.
So it records files changes, not memory changes. Or I'm trying to understand how you would replay. How would you replay an ioctal?
I don't replay. I re-execute. This is different. This is not about replay. I restart the command, the initial command, and by design, it will re-execute exactly the same thing. Since it accesses.
And it will really run the system. It will really run the system call then.
No, I don't rewrite system call.
Sorry, the system call will run when you re-execute.
Exactly.
Okay.
Exactly.
Right.
Exactly. This is not a replay. This is a re-execution.
Right. Okay.
We have a last question.
Thank you. I would like to ask if you got the same concept but for sockets. Basically, I want an application.
Can you speak louder, please?
An application that, for instance, is listening in the port 80. I want to make it listen in the port 90 or whatever. Do you have some kind of tool to remap ports, for instance, or any kind of socket stuff?
Yeah. We can use proot to remap. Yeah.
But is implemented, or should I extend proot for that?
I'm not sure.
Sorry, imagine I got an application that has a port number hard-coded. I want the application to listen in a different port. So can I use proot to listen in a different TCP port?
Yes.
But it's implemented in the tool already?
Oh no, it's not implemented. You have to specify to proot you are interested in the for instance connect system call, and then you can fetch arguments and you can modify arguments if you wish. You can do things like that. Yes.
Okay, cool. Thank you.
Do someone have another question? Okay, we have a question. Here you are.
This is a short question. Have you tried to use this tool in a security context for the security based use cases?
it can be used to, for instance, to detect user input and then to color the input and check how it is used in the executed code. It could be used, but we don't do security in my team, but could be used, yes, just to observe and to flag some external input to get a coverage where it is used and potentially where you can insert some kind of attack. No more questions?
Merci.